Have you ever wondered about the secret language of numbers, where whole numbers hold the key to unlocking puzzles? This is the world of Diophantine equations, a fascinating linguistic tool used by mathematicians. Named after the ancient Greek mathematician Diophantus, these equations have been around for centuries, intriguing scholars with their complex simplicity. Diophantine equations are not your everyday mathematical equations. They're unique, they're special. They demand solutions that are whole numbers, not fractions, not decimals, but good old-fashioned integers. It's like trying to solve a Rubik's Cube. But here, your cube is a mathematical equation, and your moves are restricted to whole numbers. These equations are a testament to the beauty and depth of mathematics, where simple numbers can create complex and intriguing puzzles. So, let's dive deeper into this unique world of mathematics and unravel the mysteries hidden within these equations. So, Diophantine equations are the secret codes of the math world, where only whole numbers can crack the code. Now, let's decode this secret language and see how Diophantine equations work. Imagine a puzzle, a riddle of sorts, where the challenge lies not in finding any solution, but in finding a specific type of solution. That's the world of Diophantine equations. Named after the ancient Greek mathematician Diophantus, these equations are a special type of polynomial equation, usually involving two or more unknowns. What sets Diophantine equations apart is that they don't seek just any solution. They seek integer solutions. So, while the equation x plus y equals z may seem simple enough, the game changes when we stipulate that x, y, and z must all be integers. The beauty of Diophantine equations is that they can have a wide range of solutions. Let's take our equation x plus y equals z. If we set z as 10, for instance, there's a whole array of integer pairs for x and y that could work. You could have 1 and 9, 2 and 8, 3 and 7, and so on. In this case, there are many solutions. But what if we tweaked the equation a bit? What if we squared x and y and set them equal to z? Now, the solutions aren't as straightforward. For instance, if z is 25, x and y could be 5 and 0 or negative 5 and 0. But what about other pairs? Are there any? This is where the adventure begins. In some cases, there could be just one unique solution or an infinite number of solutions. The challenge, and indeed the fun, is in the hunt, in sifting through the possibilities and finding those elusive integers that satisfy the conditions of the equation. So, solving a Diophantine equation is like a treasure hunt, where the treasure is the set of whole numbers that make the equation true. It's not just about finding a solution, it's about finding the right kind of solution. And that's what makes Diophantine equations such a fascinating and engaging part of mathematics. You might be thinking, why does this matter? Why should we care about these whole number solutions? Well, let me assure you, Diophantine equations are not just some mathematical obscurities. They are fundamentally important in a variety of mathematical fields and real-world applications. They're the unsung heroes of the mathematical world, silently shaping many aspects of our daily lives. Firstly, Diophantine equations hold a prominent place in number theory, a branch of pure mathematics devoted to the study of the integers. They help us understand the properties and relationships of numbers, allowing us to delve deeper into the intricate patterns and structures within the number system. But these equations are not just confined to theoretical mathematics. They also play a vital role in cryptography, the science of secure communication. In fact, the security of many of our online transactions hinges on the difficulty of solving certain Diophantine equations. The harder these equations are to solve, the more secure our data is. In addition to cryptography, Diophantine equations have found applications in coding theory, a field concerned with transmitting information across noisy channels. They help us design error-detecting and error-correcting codes, ensuring that our messages get through accurately and reliably, even in less than ideal conditions. And while some Diophantine equations can be simple to solve, others have proven to be incredibly complex and have challenged mathematicians for centuries. The famous Fermat's last theorem, for instance, is a Diophantine equation that stumped mathematicians for more than 300 years. So you see, Diophantine equations are not just a collection of mathematical curiosities. They are essential tools in our quest to understand the universe, and they continue to push the boundaries of our mathematical knowledge. So next time you come across a complex puzzle, remember the power of Diophantine equations. They are more than just equations. They are the secret language of the mathematical world, waiting to be decoded.